So today we're going to be looking at three objectives to describe the gravitational field strength at the center of the Earth or any other planet. Second thing would be to look at the resultant forces and gravitational field strengths in more complex situations when you have two or more masses. In fact, what we're doing then is treating gravitational field strength and gravitational force as the vectors that they really are. And then lastly, I'm just going to cover very briefly how to do calculations involving density. As you know from topic 2, the gravitational field strength of on an object depends on the distance from the center of the planet that you're on. If you climb a mountain, because the value of that gravitational field strength is equal to 1 over that distance squared, and here you have the relationship. As you increase this distance r, your value of g is less. So you weigh less at the top of a mountain because you are further away from the center. But what happens as you get closer to the center of the Earth? What would be the value of the gravitational field strength in the center of the Earth? And remember that gravitational field strength is force per unit mass, right? So what would be the force acting on your mass as you go close to the center of the Earth? Stop the video and have a think about that. Make a guess. Interestingly, at the center of the Earth, you literally have no force acting on you. You are weightless. As you are pulled downwards towards the center, then you find that there is more mass above you than before. So there is a resultant force, which is a combination of the force pulling you down due to the mass below you, but also the force pulling you up because of the mass above you. The resultant is a combination of those two, the force up and the force down. Remember that force is a vector, so these forces will cancel out. When you get to the center of the Earth, the net force on you is 0. There is no acceleration as you whiz with a maximum speed past the center of the Earth. So this demonstrates that there is a force value decreasing to 0 and a force per unit mass value down to 0, which then increases as you go to the other end. This is best demonstrated graphically. What we have here is a graph of force against distance using the 1 over r squared relationship. We mentioned this before when we were looking at intensity of light. The 1 over r squared curve is a very important one. And here it applies in the same way. So let's look at the graph, or how this graph will look inside the Earth. The graph shows a linear decrease in the gravitational field strength down to 0. The mathematics behind this linearity is not something you have to worry about or prove, but you do have to be clear that the endpoint at the origin is 0, and that the decrease then from the surface of the planet follows a 1 over r squared pattern. This graph is very common in multiple choice questions. Here's a fun question to think about. If you stepped into a hole that was made completely through the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience as you fell through the center of the Earth? stop the video and have a think about it. Perhaps make a sketch of your motion graph. So what were your ideas? The answer is, as you fall through, gravity at the other side would cause you to fall back again. So as you got to one side of the planet, you would then be pulled back up, right? In reality, you would oscillate back and forth approximately in simple harmonic motion. Now, I know that sounds kind of insane, you falling through the earth and then coming straight back in oscillatory motion. What's even more mind-blowing is it would take approximately 90 minutes. I guess you'd have to prove this, or the most fundamental way of proving this is to think about the relationship for simple harmonic motion. Force, or the restoring force, would be proportional to minus displacement. Thinking about the restoring force being the resultant of the gravitational force due to the earth above you, depending on below you, you could actually come up with a mathematical proof. But anyway, we'll leave that for now. Maybe it's something you can consider for your maths IA once you know how to integrate. But we'll leave that for another day. Both the gravitational force and the field strength are vectors, which means that they can be positive and negative when you are doing calculations that combine more than one of those forces. So let's consider the following situation where we have two masses. We have the Earth, which is a large mass, and the Moon, which is a smaller mass. Now, if I place an object here, more or less between the two, there will be a force acting towards the Earth and a force acting towards the Moon. According to this diagram, as you can see, X is more or less in the middle. It's actually closer to the Earth. Then the force due to the Earth would be bigger than the force due to the Moon. So when we're working out the resultant force, we would just subtract, choosing an arbitrary positive, which in this case, I'm going to choose Earth as an arbitrary positive because it's the largest one. And then I would work out the resultant in the same way as in topic 2. Your resultant force would be equal to the force due to the Earth, the force due to the Earth's gravitational field, minus the force due to the Moon's gravitational field. Your resultant would be the result of that calculation. Now, an interesting thing happens when we consider point P, and this always happens. This is very much the case between any two large masses. At point P, which is a point you would have to calculate very carefully, but at point P, you have no resultant force or field strength. Why is that? Because at that point, the force due to the Earth is cancelling the force due to the Moon. These two forces are equal. And at that point, there is no force acting. You could literally float at that point, right? And that point does actually exist. This can lead to some interesting calculations where, not knowing where the distance is, you can use your gravitational field calculation, your gravitational field formula, to work out the distances are by using simultaneous equations sometimes. There'll be an example of one of those later. But that is the second type of question that you'll come across. Now, remember that gravitational field strength is simply force per unit mass. So if you want to consider the force per unit mass acting at this point, it's exactly the same. The force per unit mass means that you disregard this mass. You don't need to worry about that mass. And so therefore you would do the same calculation. The gravitational field strength due to Earth minus the gravitational field strength due to the moon would give you your resultant. That should be a G, gravitational field strength due to the moon. And that will give you your resultant force per unit mass, gravitational field strength on P. Same here, because the two forces are equal, the gravitational field strength is also equal. So the gravitational field strength of the Earth equals the gravitational field strength on the moon, of the moon, on P. So therefore now you can build your equations. R1 squared equals GM over R2 squared. Okay, that would be mass of the Earth for the first one. And R1 would be this distance, right? And then you would have mass of the moon, which is, and then relates to R2, which would be this distance, the distance from the moon to the object. Okay, so this enables you to do some really simple calculations. Graphically, your field strength diagram looks like this. As you go from the surface of a planet towards that point P on the diagram previously, literally following a curved relationship down to 0, and then you're doing a curved relationship back to the second mass. Try and think why one of these is positive and one of these is negative. The positive and negative signs in this graph demonstrate the direction of the force acting. So in the first part of the graph, the force is acting here towards M1, which is the opposite to what we've considered to be positive. And as we approach P, as we approach 0 field strength, then we find that as we go towards M2, the force per unit mass is now positive, right? So it's negative and then positive. Let's try this out with a question. In this diagram, P is a point midway between the centers of planets A and B. At P, the gravitational field strength due to A is 4, and due to B is 3. What is the gravitational field strength at P? And we'll leave part B for now. Okay, so just work out the gravitational field strength at P. Hopefully you got -1. Okay, if you decided to choose +1 because you used a different polarity, you used a different convention, then your answer is still correct. So now to finish off, I'm just going to give you a short explanation on this idea of density. When we're using the GM over R squared relationship for gravitational field strength, or GMM to look at the force that's acting, we can actually use density values instead of mass values. So the important thing to understand or remember, bringing in from previous study, is that mass is equal to density multiplied by volume, right? So I like to remember it like this. It makes more sense to me. Density, the amount of mass per unit volume, is equal to mass, surprise, surprise, over volume. The second factoid that you need to bring with you, although it is in the data booklet, is that the volume of a sphere is 4/3 pi r cubed. So if we know the radius, which we usually do, because that's a very important value in gravitational field questions, we can find, using this equation, 4/3 pi r cubed, we can find volume. And if we're given density, we can find mass. We could substitute it in together to give you a proof for this relationship, which I think is a little bit insane. I think it's a bit of an insane equation. I think it's easier to just remember that density equals mass over volume, and then substitute that into G equals GM over R squared. Okay, but you can derive an equation using this if you wish. Okay. And that's it for today's work. Have a go at the questions and look at the answers, the derived answers.